we're in section 5.7. We're going to look at some, wow, can you believe it? Some more techniques, additional techniques for integration. And what we have here is a trigonometric integral. A trigonometric integral. And of course, this here means the cosine of x to the 5th power. Okay. Okay. So trigonometric integral. All right. Well, are we used to seeing the cosine of x to the 5th power? Are we used to seeing the cosine 5th x in our trig classes and so forth in our math? Are we used to that? What are we used to in terms of like a cosine to a power? What's something that I mean, we've seen a cosine of x to a power before, but what power is it?
Squared.
Okay.
Squared.
Squared. Oh, okay. So what? Cosine squared plus what so like you have your half angle identity formulas. You have trig identities that give cosine squared of x. What other? You have another identity.
Sine squared plus cosine squared equals 1.
That's right. Good. Good, Samuel. Right. Right. So, okay, you know, we really have to take this function and break it down. We have to break it down. And we can also utilize this too. So watch what we do here. Watch what we do. I'll go to the next page. I'm going to take the cosine of x to the 5th power, and I'm going to write it as cosine of x squared, which I like, times cosine of x squared, which I like, times cosine of x. I mean, I can rewrite the integral this way. And then we can make use of this Pythagorean theorem. Since sine squared plus cosine squared equals 1, that means these cosine squared terms here can be replaced with 1 minus sine squared. Okay, here, here. And this, in fact, helps us a lot because now we can make a substitution. Because the sine of x is related to the cosine of x. The derivative of the sine of x is the cosine of x. So when we write our integrand this way, and we have functions related to each other, we can use substitution. Absolutely fascinating, really. So I'm going to let u equal sine of x. Du dx is cosine of x, so du is cosine of x dx. Question, Samuel.
So in a case like this where you have two functions or two formulas with, or whatever, with sine x, does it really, you only equate u to one sine x and not two?
Well, I see, I don't want to let u equal cosine of x. I mean, let think of it like this, and your question's a very good one. These are the more complicated terms, right? These 1 minus sine squareds. So if I let u equal sine of x, it makes then you know, these terms like become easier to work with. Do you see how I'm going from this integral to this integral?
Yes.
So that's the way we wouldn't want to let u equal cosine of x, because it would be just, it's just better to do it. It's just the right way to do it this way. And then look, of course, the limits, the 1, where are we getting the 1 from? Well, that's the equal
Cosine
to
pi squared.
Well, but look at our substitute.
Sine pi squared.
How about sine of pi over 2?
What am I saying? I said pi squared, didn't I?
You did, but that's okay. You're participating. And then so the top x limit was pi over 2. We're going to make that equal to 1, because, well, the sine of pi over 2 is 1. And then the bottom limit, x limit, was 0. And the sine of 0 is just 0. So we end up now with an integral with respect to u. We used foil, and then we can FOIL. I mean, we got now, what's this? What is this? What kind of function is this? 1 minus 2u squared plus u to the 4th. What kind of function is that? What do we call that? It begins with a P.
A polynomial.
Polynomial.
Polynomial. Okay, that's easy to integrate. You learned how to do that in Calculus 1. All right. Are there any questions up to here before I go to the next page? Okay. Who's feeling? Maybe give me a thumbs up if you're good. If you're Sean, question? All right, good, good. Excellent. Okay. Excellent. Well, then here we are. We'll just get the antiderivative of this polynomial, and we'll substitute in 1 and 0, and we're good to go. We'll get 8/15. So then our definite integral equals 8/15. All right. Are there any questions before we move on? All right. Let's look at another problem. Wow. How many are looking at this integral and saying, oh my goodness, we're going to find that antiderivative? All right. Yes, Samuel.
Is this going to involve any cancellation or factoring out at all?
Well, we can't. Your instincts are good about the factoring. There is, you can see that the denominator here can be factored, right? The numerator can't be factored nicely, but the denominator can. But no, we can't cancel any x's out because, you know, algebra says there's no like multiplication going on. What we have to do is rewrite this. Rewrite this. We have to rewrite this rational equation, because we certainly can't integrate it the way it looks now, right? I mean, we can't. So we're going to use an approach. We're going to use an approach called partial fractions. Okay, and I'll write that here. We're going to use, this is a very important approach. You'll see it in differential equations too. You're going to use the approach called partial fractions. First, though, we're going to factor the denominator. So, all right, next page. I factor the denominator the best I can. I'm not worried about the numerator. It's the denominator I'm worried about. So, okay, how does this work? So again, we have to rewrite this rational function. It turns out that the rational function can be written, well, there are two factors in the denominator. There's a linear factor, which is the x, because that's of degree 1. And then there's the quadratic factor, which is x squared plus 4. Now that's second degree. It turns out that you can write the rational function as the sum of these two functions, two rational functions. The first rational function or fraction has the x, the linear factor x in the denominator. The second fraction has the other factor x squared plus 4 in the denominator. The degree of your denominator determines what you put in the numerator. So since x is a polynomial of degree 1, we put a constant a up above it. So a constant is of degree 0. If you remember polynomials, how many remember like degrees, like a polynomial of a second degree, third degree, fourth degree? Yeah, that's all we're doing here. The x here is a polynomial of degree 1. So above it, we put a constant, which is 1 degree less. That's a polynomial of degree 0. The x squared plus 4, what's the degree of that polynomial? X squared plus 4, what's its degree?
2.
2. So look what we put above it. We put a linear expression, b times x plus c. That's 1 degree less. So it turns out, I mean, if we could somehow solve, if we could find the values of a, b, and c that will make this equation true, then we're going to have a much easier. It's going to be. We'll be able to integrate this on the right. So what do we do? What do we do? Okay. Well, what we're going to do is we're going to multiply by the least common denominator. So this is what's called a rational equation. We want to reduce the rational equation into just a normal kind of equation, polynomial equation. And to do that, we're going to multiply by the LCD. How many remember LCD, least common denominator, from maybe Algebra 2? Sure, sure. Well, okay, so I multiply by x times x squared plus 4. So on the left-hand side, the x's simplify out, and the x squareds plus 4 simplify out. And that leaves me with 2x squared minus x plus 4, and that's what I have right here. Now on the right side, I'm going to distribute my least common denominator. I'm going to multiply it by both of those terms. And so when I multiply x times x squared plus 4 times the a over x, what's going to simplify out? The x or the x squared plus 4? I mean, I tell you what I can do, let me just kind of, this pen gets out of control a little bit, hold on, but we're okay. So I have a over x times x squared plus 4 plus bx plus c hold on. I'm trying to write this the best I can. Hold on, I'm going to do this again. Okay, I've justified the left side. Let's justify the right side. So we're distributing this to both of those fractions. So you have a over x times x squared plus 4. That looks better. And then you have bx plus c over x squared plus 4 times x squared plus 4. Okay, you're going to have simplification here. You're going to have simplification here. And that's going to give you, then on the right-hand side, a times x squared plus 4 plus bx plus c times x. Are there any questions up to this stage here? All right. Well, it seems natural on the right-hand side to expand the right-hand side out. So I'll get ax squared plus 4a plus bx squared plus cx. But then what I'm going to do is I'm going to combine terms. Ax squared plus bx squared is a plus b times x squared. Right? And then you have, so that takes care of these two terms. The ax squared plus bx squared equals a plus b times x squared. The 4a is just the 4a. And the cx is just the cx. Are we good up to here? All right. Well, now what we want to do is we want to solve, very good, Nicole, excellent. What we want to do is we want to solve for A, B, and C. So I'm wondering, based on this last equation here, you know, what would A plus B have to equal? What would C have to equal? What would 4a have to equal? If we, you know, we have an equation here. So the right-hand side of the equation has to be equal to the left-hand side. So like, okay, hold on here. So Jacob says C has to equal -1. That's right. That's right. So hold on, let me make this a little. Looking here, right here. So a plus b would have to equal 2 because the x squared term has to equal the x squared term. If I got a polynomial on the left equaling a polynomial on the right, the like terms have to be equal. So 2 has to equal a plus b. Okay. And then we got a -1x here, so -1 has to equal c. And then we have a 4. 4 has to equal 4. Sorry. 4 is going to equal 4a. Are you seeing this okay? Is that good so far, what I wrote? Makes sense. Good, good. All right, well, let's go to the next page then. I have this written on the next page. So, okay. C is going to equal, well, the fact that A, since 4a equals 4, A is going to be 1. But if A is 1, the fact that A plus B equals 2 means that B has to equal 1, and C has to equal -1. And so now we're able to rewrite our integral in this much easier form. And the integral of a sum is the sum of the integrals. Okay, take a look at that. Okay, let me know if you have any questions. Okay, so now our integral, now I'm right here. And this integral on the right here, the integral of x minus 1 over x squared plus 4 dx, I can split that integral up, right? This is a fraction here, right? I can write that fraction as the difference of these two fractions. With that common denominator, and so my integral now equals this at the bottom. Please let me know if you have any questions. Yes, Samuel.
That last part is our final answer?
Oh, no. We have to do these integrals. So let me ask you this. Is this integral here an easy one? What's that? What's the antiderivative for the first integral?
ln natural log positive x.
Right, the natural log of the
absolute value of x.
Right, the natural log of the absolute value of x. And for this second integral here, what can we do to get the answer on that integral? What technique can we use to work that one out?
Use substitution.
Use substitution. Use substitution. We don't want to mess with division on that. Jacob, you're thinking of differentiation for the quotient rule, but we're doing an integral here. So we're going to do use substitution. And then the third one, the third integral, is going to require a formula. And the formula is actually in your textbook, but I'll show it here. So if there aren't any, are there any questions before I go to the next page? All right. Okay, so for the third integral, so for the second integral, I'm going to let u equal x squared plus 4. Okay. I'm going to do a substitution, and that will work. For the third integral, we need a formula for that. Now, we can actually derive this formula using what's called trig substitution, but we're not going to worry about that here. There's a general formula that says the integral of the fraction 1 divided by the denominator x squared plus a squared. That'll equal 1 over a. That antiderivative will be 1 over a times the arctangent of x over a plus a constant. So for our integral here, what's a going to equal?
Two.
A equals 2. That's right, because 4 4 equals 2 squared. And that goes with the a squared. And this is a formula you'll need to memorize. Another antiderivative formula. Okay, and then we get down to here. Let me know if you have any questions. Okay, and so now, incidentally, this second term here, would it be okay to write the second term as just the log of x squared plus 4, where we just drop the absolute values? Would that be all right?
Yes.
It would.
Yes, because it's always positive.
That's right, because it's positive. So sure. So I'll put the final answer on the next page, but I want to make sure everybody's comfortable. Are we all good with this? Okay, Nicole, no problem. Yeah, if I were in front of you looking in the classroom, I could see, you know, but it's a little different remotely. Jacob, question? Oh, you're good. Okay.
No, I had a question. I was wondering if you had like more degrees, like if I went up to like the 5th degree, would you just keep going through the letters? So like a, b, x squared, c, x cubed.
You would. I've never seen one with 5th degree in practice.
Oh.
You know, at some point you would need probably your computer to help you, you know. But for our problems, we'll keep it simple. But yeah, it can go, you know, the theory extends to, and you know, for all the homework now you're doing, of course you're working that out by hand. You know, I'm going to want to see your work, and I might, you know, again, I'm going to work this out. But see, you can upload your work, like when you take your WebAssign exam, you can upload your work during the exam. You know, now I might have to give you a little extra time so you can do that, but you know, the work, you snap a picture, upload it during the exam time, and it's right there. You know, so you know, but yeah, this here, you just these problems, Jacob, they'll keep them simple enough so you can do them by hand. Yeah.
Okay, thank you.
You're welcome. Are there any other good questions? All right, let me go ahead then, and here's the final answer. All right, are there any questions at all?
Professor, can you go back last page?
Go back one page before, okay.
Yeah, I just have a question about the formula. The formula
Okay.
one. Yeah, so why is 1 over a? I thought it should be 1 over a square.
Oh, you mean, okay,
The right side of the formula.
this one here. Yeah, that's just it's a formula that that the book just gives you. They don't prove it. They don't prove it at all. They
Yeah,
just
I just tried to prove. I thought it should be 1 over a square, and it's because so for the denominator and the numerator both divide to a square, right? So you got
let's see,
the
I want to make sure. So you are talking about this formula, right, Leping?
yes, and I thought the right side of this one is 1 over a square.
No, oh no, okay, hold on. Let me no, it's so this is the formula.
Yeah, just this a. I thought it should be a square.
No, it's just A. Just A.
Oh, I don't understand why it's just a.
Well, there you have to derive it. You have to derive it. Take it on faith. Take it on faith for now. Yeah, to prove it,
Okay.
to prove it, we would need to do something called a trig substitution. But we're not like going to do that right today. But take it on faith for now. But I admire that you want to know why it's true. It is, yeah. I always like to know why things are true. This one, just take it on faith. And, all right, very good, very good. Are there any other good questions? All right, let me stop the recording.